Greetings and welcome to Physical Science at Hack. The purpose of this video is to go through some of the sample problems for Chapter 6 on electricity. And we will work through some sample problems here, and you will see some similar problems when you work on the homework and problem set for this lesson. So we'll start off with the first one. First question states that one rubber balloon with a negative charge of 3 times 10 to the negative 14th coulombs is suspended by a string and hangs 2 centimeters from a second rubber balloon with a negative charge of 2 times 10 to the negative 12th coulombs. And our first question asks, what is the direction of the force? And we know that because this is a negative charge here, and this is a negative charge here, they're both negative charge, we know that like charges will repel. So the force is going to be a repulsive force. The force is pushing them apart. So that's part A. Now part B is the one that will actually require the calculation. So let's see what we get here. Let's write down our numbers that we know. And we know that the distance is 2 centimeters, which is equal to 0.02 meters, which is what we're really going to need. You've got to watch the units there. That's given in centimeters because it makes a little more sense to discuss it that way. But in terms of the calculation, we need that in meters. We also know the two charges. Q1 is 3.00 times 10 to the negative 14th coulombs. Q2 is 2.00 times 10 to the negative 12th coulombs. And we know one more thing. We also know the constant that we're going to need, and that's K is equal to 9.00 times 10 to the 9th Newton meters squared per Coulomb squared. So that's what we're going to need to be able to determine the force. So let's get the force figured out here. We know the equation for force. Force is equal to K, Q1, Q2 over D squared. So let's put in the numbers that we know. We know what K is, 9.00 times 10 to the 9th Newton meters squared per Coulomb squared, times the two charges, which is 3.00 times 10 to the negative 14th coulombs, times 2.00 times 10 to the negative 12th coulombs, and all of that is divided by, and in meters, 0.02 meters squared. So that's what we have so far, and let's go ahead and do the calculation now. If we multiply the numbers in the numerator, we find that that is equal to 5.4 times 10 to the negative 16th divided by 4.00 times 10 to the negative 4th. Now let's look at our units here. And our units were Newton meters squared per Coulomb squared in the numerator times coulombs, and then divided by meters squared in the denominator. So the meters squared canceled, and these two coulombs cancel the Coulomb squared, and we get a force just in newtons. And when we divide these two, we'll get our final answer, which is 1.35 times 10 to the negative 12th newtons. So then we will get our final answer there, and that is what we are looking for. That is the force between these two balloons. Now our second problem talks about a current. So we're looking at an electric current passing through a wire, and 6 coulombs pass through every 2 seconds, and we want to know the magnitude of the current. Well, let's write down what we know. We know the amount of charge, Q, is equal to 6.00 coulombs, and we know that the time is equal to 2.00 seconds. Now, we're looking for the current, and from our text we know that the current, I, is equal to Q, the charge, divided by the time. So the amount of current is just the amount of charge divided by the time. And in this case, that is 6 coulombs divided by 2 seconds, or 3 coulombs per second, which we know that's 3 amperes. So 3 amps. The current would then be 3 amps for this situation, this electrical current here. So that would be our answer in this case. Now our third problem talks about the current. Again, we have a current. We have the current in a 60 ohm resistor, and the potential difference across it is 120 volts. So again, let's write down what we know. We know that the resistance is equal to 60.0 ohms, and we know that the voltage is 120.0 volts. So those are the two things we know. Now, what is our equation for this one? We're trying to find the current. And we know that the voltage is equal to the resistance times the current. We're looking for the current, so that can be solved to show that current equals voltage divided by resistance. We know those two, so we can go ahead and solve this. The current is equal to the 120 volts divided by 60 ohms, which equals 2 volts per ohm, and that is, if we go ahead and do that, that is actually equal to amps. So that's 2.00 amperes for our answer. So the current through this resistor would be 2 amperes. Now our next problem looks at a hairdryer. We have a 1200 watt hairdryer being operated on a 120 volt circuit for 15 minutes. We know the cost of electricity at 10 cents per kilowatt hour, and we want to know the cost of using the blow dryer. So, as we do, let's write down what we know first. What do we know in this problem? We know, first of all, that the wattage is 1200 watts. We know that the time that we're using for this is 15 minutes. Now, what units do we use here when we talk about kilowatt hours? We're not talking about kilowatt minutes, we're talking about kilowatt hours, so we need to convert this into hours, and that is 0.25 hours. 15 minutes is a quarter of an hour. And then we know the rate of 10 cents per kilowatt hour. So those are the three things we know. Now let's go ahead and get our equation here. And this was equation 6.7 in this textbook. And it says that the cost is equal to the number of watts multiplied by the time multiplied by the rate and divided by 1,000 watts per kilowatt to convert the wattage into kilowatts. So we know everything here. What is our cost? The wattage is 1200 watts. The time is a quarter of an hour, so we multiply that by 0.25 hours. The rate is 10 cents per kilowatt hour. And we divide that by 1,000 watts per kilowatt. So what are we going to cancel here? Let's see what's going to cancel and what we're going to get with this problem. And if we multiply all of those numbers together in the top, what do we get? Well, let's look at our units. Let's see what cancels here. We can cancel the watts, we cancel the kilowatts, and we cancel the hours. What's left? It looks like everything canceled. Well, we have to remember that this is actually dollars here, because really what we're looking for is the cost. So then if we multiply all of these numbers together, we would find out that this is equal to 3 cents. $0.03 or 3 cents would be the amount, the cost that it would take to run this hairdryer for 15 minutes. So you can do a calculation like that. Now finally, let's look at our last one here. Our last one says that two 8-ohm bulbs, light bulbs, are connected in a 12-volt series circuit. What is the power of both glowing bulbs? So let's see what we know here. Let's write down our numbers. We know that the resistance is equal to what? The resistance is 8 ohms, but there's 2 of them. So there's going to be 2 of those. So when we initially look at it, the resistance total is going to be 16 ohms. And then we'll have to look at them individually in a minute. We know that the voltage is equal to 12 volts. So what is our first thing? We're looking for the power. Power is equal to current times the voltage. So we need the current and the voltage. But we need to know them across each of these individually. So first we want to find the current. The current going through a series circuit will be the same for each object. There will be some amount of current. And we have to find out what that current is going to be. So the current is, how do we find that? We know that, again, voltage equals resistance times current, or current equals the voltage divided by the resistance. So that's equal to the 12 volts divided by the total resistance. So this is total resistance, which is going to be 16 ohms. So 12 divided by 16 gives us the current through this circuit of 0.75 amps. Now that's not the number that we need though. That's the current. That gets us started, but what is the voltage that we need? The voltage that we have here is 12 volts, but in a series circuit, the voltage drop across each object is not going to be 12 volts. In a parallel circuit, it would be. In a series circuit, each one will not be 12 volts. They will have to add to 12 volts. But let's double check that by finding out, by working again with Ohm's law equation here. And now we want to find the voltage is equal to the resistance times the current. We figured out the current, so we can go ahead and say that the voltage across each of these is equal to the resistance on one, 8.0 ohms, times 0.75 amps. So the voltage is going to be then 6 volts across each of these two. So what we're going to find is that it's 6 volts across each. Now that makes sense because it will add to 12 volts when we add the two of them together. So the total voltage drop must be the total potential difference. But across each one, it would have to be the same. So it would be the same because they're the same resistance. Now if they were just different resistances, you'd get a different voltage for each of them, and you'd have to do the calculation a little differently in that case. So we now know the voltage drop across the resistor here. We know the current through through the light bulb here. And we can then say that the power is equal to 0.75 amps times 6 volts. So the power drop across each resistor would be 4.5 watts for each bulb. So the power of each of an individual bulb would be 4.5, and you'd have to add that together or get 9 for the total power of both bulbs. But this would be how much each of them is, and in this case, because they're both the same resistance, then it would be exactly the same. So that concludes our working of the sample problems for Chapter 6. Again, you'll be able to look at some of these, and you will be doing some similar problems coming up in the homework and problem sets. So until next time, have a great day, everyone, and I will see you in class.